In this final video of my reflection on the power, momentum, and impulse summative, I'm going to just go over the final page, the last three problems. And these are three computations that we had to do. The first one here, problem number 3, it says, what is the average power required to accelerate a train with a pretty big mass, a train locomotive, from rest to 17.0 meters per second in 23.0 seconds. So I list the things that I know in this problem and the thing that I'm looking for. I'm looking for a power, and I just chose the units of watts because that's my SI unit. I've written down the mass of the train, the initial and final speeds of the train, and the amount of time that it took to achieve that change in speed. And there's a couple different approaches to this problem, actually, and the one I chose to make was, first of all, to start with my basic definition of power, and then acknowledge, like, I know the time and I'm looking for the power. I just need to figure out what to do about this work. Because in this problem what's really happening is the train's kinetic energy is changing, I use the work kinetic energy theorem, which just tells me that whatever work is done on an object is going to be equal to its change in kinetic energy. And of course, I need to know the definition of kinetic energy, which I have right here. So putting all this stuff together, I just start with my power equation, and then I substitute the change in kinetic energy for the work, and I can expand that into the final kinetic energy minus the initial. And that initial kinetic energy is just 0 because the initial speed or the initial velocity is 0. So I'm left with this relationship. I cleaned it up a little bit by putting my 1/2. I'm just dividing by 2 instead of multiplying by 1/2 here. And now I can just substitute all the numbers into this formula. The mass, the final speed, divided by 2 times the change in time, which is 23 seconds. And when I do that calculation, I get 168,000 watts. And I chose to just represent my answer in kilowatts because it's just a nice number of kilowatts, I guess. But I think that one of the things that's challenging about this problem is that you've got to figure out how to handle this work term and how to get work from the information that was given to you. I chose to use the work kinetic energy theorem to do that. In problem number 4, we've got a parachutist with a mass of 82 kilograms total, falling straight down. Okay, that's an indication about the direction at a constant speed of 55 meters per second. And she opens her parachute, and then it takes less than a second, just 0.84 seconds, for the parachute to slow her down to this safe landing speed of 4.5 meters per second downward. So she is decelerating. Her speed is decreasing. But she's still falling down in both cases. And so we just notice the direction of those two velocities that we were given. And I did include that information when I wrote the initial and final velocities over here. In fact, what I'm really doing over here is saying that I'm considering the positive direction to be downward, because I said that VI equals 55 meters per second down. And if I said negative 55 meters per second, then that would be saying that up is positive and down is negative. So anyways, I've done something implicit by not including a negative sign here. And that is going to come out in the math a little bit later. This is a pretty straightforward application of the the impulse momentum theorem, which is stated right here. And for good measure, I just put the definition of momentum because I'm surely going to have to plug in some velocities and some masses in order to get this change in momentum. So the first thing I did over here I took the original equation, and let me fix this. I divided both sides by delta t, and those cancel out. And I'm left with this relationship. The force that is the net force acting on the parachutist is going to be equal to the change in momentum divided by the amount of time that it took for that change to take place. And I substituted in for the change of momentum the final momentum minus the initial momentum. And when I actually substitute all the numbers into this equation, I end up with a negative 4,900 newtons. And just to be clear, because the initial speed is greater than the final speed, that's where that negative sign comes from. But it's good to interpret the meaning of it when we finalize our answer. I said that downward is positive, and so what this means is that there's a 4,900 Newton net force acting in the vertical direction upwards to slow her down. Another approach to this problem that some students decided to take was instead to use F equals ma, Newton's second law, and then the definition of acceleration, constant acceleration, which is F final minus, or V final minus V initial divided by the change in time. And if you're careful about combining these two equations, you'll see that if I just substitute this acceleration in for A right here, I pretty much end up with this relationship. And there's a good reason for that. The momentum impulse theorem is derived from Newton's second law. So surely you can solve this problem just by using Newton's second law and the definition of acceleration. So now, I did in this case, while I didn't do this on the easier problem, it was important that people acknowledged that there was a particular direction to this force. In this case, it's either negative, or in other words, opposite from these velocities, or you actually indicated what direction the force was acting by interpreting the problem. So you can lose a half a point if you don't consider the direction of your vectors, so be careful with that. Okay, this last problem is pretty challenging, but it's also very much related to a couple of the problems that we did in class, and so I felt like it would be a really good assessment of whether students really understood those problems, both from the book and from the slides that were similar to this. I'm going to talk a little bit about why this problem is hard and how we can get around that, or how we can think about it. We got a cliff diver over here. We have an image. I drew a little diagram here myself. And what's happening is they're leaving the cliff here at point A. They're jumping up, and they achieve some maximum height, and then they fall. And right here, they go into the water. And then once they're in the water, then they slow down. So there's really like 3 interesting points. This makes it a little bit challenging to use like final and initial subscripts, like the final mechanical energy is equal to the initial mechanical energy, because we have 3 different points, and so we got to be really clear about what points we're comparing. So that's one important issue here. The second thing is, let me just go through and make sure I understand all the information that was given to me. I know that a cliff diver with a certain mass jumps off this cliff. The cliff is 12 meters above the water, and he jumps off with a 3 meters per second speed. And once he's in the water, a net force on the diver of 1,100 newtons is acting in the opposite direction of the motion. That is, it's causing him to slow down. How long does it take the diver to come to rest? So we're looking for a time. So maybe I'll add that right here. I'll just say like delta t equals question mark. So I've collected all the information here, and notice I'm using these subscripts h sub a, v sub a, to indicate the speed, the height, and the velocity at this point A. I know that at point C, at the very bottom, he's coming to rest. So that's interesting. And then finally, I've got a force that the water is applying on the person, and I just put a negative sign here to remind me that it's acting in the opposite direction of the motion. In other words, the opposite direction of the speed when he enters the water. So there's a lot of equations that I use to solve this, but first of all, it's really broken into 2 parts. I need to use conservation of energy to determine how fast this person is going when they enter the water. And then I have to use, I decided to use the momentum impulse theorem, because I know that the momentum of this person is changing as they slow down and come to rest. And because their momentum is changing, then I can compute the net force that's causing that change. That's given to me, and I can use that to find the time. So this is really the fundamental sort of center of my work here. I'm looking for delta t. I've been given F, and I can probably figure out how the momentum of this person is changing as they slow down in the water from point B to C. So what I did first was I'm just comparing the mechanical energy at points A and B, and that aligns with the hint that I gave here as well, by the way. Mechanical energy is conserved when the diver is in the air. At first, at point A, they have potential energy and kinetic energy because they're moving and they're above the surface of the water. When they enter the water, their potential energy is 0 because I'm measuring my heights from the water surface. So they only have kinetic energy. So if I substitute the formulas in there, being careful with my subscripts, the masses cancel, and I can solve this relationship for the speed at B, which I did here. I kind of broke one of my rules here, but I thought it would be a little more straightforward if I just substituted all these values into this formula in order to get my actual speed at B. And what I did, by the way, was I kept 4 significant digits here because I'm going to wait to do my rounding until the very, very end. So I wanted to leave enough information here so that when I round, I don't introduce any error. Okay, but now I can use my momentum impulse theorem. I can solve it for the change in time, which is what I'm looking for. And then I know that the change in momentum from point B to point C is going to be whatever momentum we ended up with in the end, 0 because he comes to rest, minus whatever momentum he started with, and I can figure that out too because I got that velocity. And I'm dividing by the force, in order to end up with the change in time. So when I do this calculation, I get a negative divided by a negative, which is a positive. That's helpful because we know that he's going to land a certain amount of time after he jumps. And this is the number I get, just less than 1 second. And I just rounded to 2 significant figures here because that's really all I'm allowed from this problem. So, but just to recap, this is a 2-part problem. First of all, conserve energy to get the speed that he enters the water, and then use some kind of momentum, or just like in this problem, you could use the force, you can use Newton's second law, in order to figure out how long it took for him to slow down, to come to rest. So energy conservation plus momentum, and that's what makes this a challenging problem.